All right, so today we'll be talking about section 1.5 in the book. The main topic in section 1.5 is analyzing the graphs of functions. So I will expect you to be able to do that by the end of these videos. Additionally, we'll be talking about even and odd functions and how to show that the functions are even and odd using algebraic methods. So to start off with, I want to talk about even and odd functions. So essentially what we're going to be doing here is returning to symmetry, which was covered in section 1.2. Except now we're going to be doing it using a functions standpoint. So we're still going to have, we're still going to have y-axis symmetry. For example, we could look at the function a parabola. This could be, let's say, 1. Maybe this is the function f of x equals x squared plus 1. So here's an example of a function with y-axis symmetry, and we'll still talk about origin symmetry. For example, we could look at, I'll just do a cubic as kind of the classic. So this could be a function f of x equals x cubed. So these are two types of symmetries we can look at with functions. Note that we cannot do x-axis symmetry, because if you have a graph that has x-axis symmetry, for example, we've seen this one before, this is not actually a function. So this might be something like y squared minus 5, I believe we had before. This is not actually a function, so therefore this will not be part of the conversation today. All right, so let's now talk about an even function. So an even function is any function whose graph is symmetric across, across the y-axis. So for example, that parabola we just created would be an example of an even function. Because it's symmetric across the y-axis. And an odd function is any function whose graph is symmetric on the origin. So for example, the one we just graphed was f of x equals x cubed. So this would be an example of an odd function. Okay, so graphically, not too bad. It looks a lot like what we did in section 1.2. We have y-axis symmetry and origin symmetry. So now let's talk about the algebraic method of showing symmetry. And in order to do that, I'm first going to give you kind of the rules here. So for algebraic, when we replace x with negative x, this is what we talked about in the symmetry section, the equation remains unchanged. And the way we can write that using function notation, actually I should say, so if this is true, then the function is even. And so what this means with function notation is if I have f of x that should be the exact same as f of negative x. So if this is true, then the function is even. So this is a rule you might want to have highlighted or something in your notes. That is an important rule. Now, for the origin, it's a little bit different because with the origin, we said we needed to replace x and y. But we don't really have a y here because we're talking about f of x, so I want to keep this in function notation. So let's say we replace x with negative x. And if you do this and the function change signs, then the function is odd. I will do an example of this in a moment. So if it's not exactly making sense right now I'm just giving you the rules, and then we'll do an example which will hopefully clear up any questions you might have. So notationally speaking, we would say if I take f of negative x, so I'm replacing x with negative x, and it gives me f of x, except for it's now negative f of x, then the function is odd. So this is the other rule. So we essentially have two rules we'll be looking at in this video. One for even and one for odd. Okay, so I'm going to show you kind of a full example of each of these. So let's show that f of x equals, let's do x cubed minus x is odd. Okay. Now, regardless of if it's odd or even, your first step, you might want to maybe make a note here, your first step is to always do this, f of negative x. Notice that in each of the rules, we eventually have to do f of negative x anyways. So always figure out what f of negative x is first. So if I was doing this problem as a student for Mr. Edwards, I'd say, all right, the first step I'm going to do is f of negative x. Replace all the x's. And at this point, hopefully, we're starting to become experts at this. Negative x cubed is equivalent to, let's kind of make a note on the side here. Negative x cubed is equivalent to negative x times itself 3 times. And so that actually comes out to negative x cubed in this format. So I'll replace that one. If I subtract negative x, that turns into a positive x. Notice this is not the same, you could even say that, not the same as the original. So we actually can immediately conclude that this is not even. However, that not even does not mean the same thing as odd. You can have functions that are both not odd and not even. So we still have to show that the function is odd. So the next thing I'm going to do is figure out what negative f of x is. Because that's what the definition says. I have to do negative f of x. So I'm going to take a negative sign and drop that in front of my function here, which really means I have to distribute a negative 1 to each term. So I end up with negative x cubed plus x. And at this point, it's a good idea to actually show me. So please actually say at this point, same. So if I'm grading your work, I noticed that, yep, you noted that they were the same. So then you could conclude, so you could say f of x is odd because f of negative x equals negative f of x. And that would be the final answer, and we have our work to prove it. Okay, let's try an even one now. And I'm actually going to change this problem just a little bit this time. So rather than telling you to prove something is odd or even, I'm just going to ask, what is it? So the question here is going to be, is the function f of x equals, let's do negative 3x squared minus 2x to the fourth plus 8. I'm going to say, is that even, is it odd, or is it neither? Even or odd. Okay. So now you don't actually know if you're trying to prove whether it's even or odd, but that's okay, because no matter what, our first step remains the same. Let's go up here in the notes real quick. First step, I'm going to circle that, highlight it if I can. This is really, really important. The first step is do f of negative x, no matter what. So here's my pretend student doing the work now for Mr. Edwards. Negative 3, I'm going to replace x with negative x. And at this point, based on your knowledge of what we've done before, you might immediately start to recognize now that this will just be x squared. This one is just going to be x to the fourth. And then we have plus 8. So at this point, you take a look and you say, you pause and you say, okay, this equation and this equation, the original, are those the same? Take a quick look. Looks to me like they're the same. So then you would say f of x is even because f of negative x equals the original equation. And in the beginning we said that was the rule. If f of negative x is the same as the original, then the function is even, and so you would be done with that problem. Notice I actually stopped once I got to even. I don't even have to check odd, and I definitely don't have to check neither. So a function is almost never going to be even and odd. There is one function that would work, and that's the line y equals 0. But other than that, I don't think anything works. So once you find that it's even, you can stop. Let's try another one and make it a little bit more, have a few more steps to it. So we're going to ask the question is, I'm getting kind of tired of f, so I'm going to say m of x is this function, x cubed plus x divided by x squared plus 4, even, odd, or neither. And with these problems, I really should add show algebraically, because if I don't add that, you might be able to just graph the function and tell me if it's even, odd, or neither from that. But I'm really focusing here on the algebraic work and the algebraic manipulation of equations. Okay, so once again, the first step, we're going to replace x with negative x. So if you forget everything else, please don't forget that first step. Okay. So here we have it. We are going to take this one step further. Negative x cubed. If I add a negative x, that's the same as just subtracting it. And then in the denominator, negative x squared is the same thing as x squared. And so I have this. Okay, we're going to pause. Let's take a look at the original up here. To me, it looks like this is not the same. So I might either say not the same as the original, as m of x, or you might just say does not equal m of x, like that. I would probably do it this way because I don't like to write too many words when I can help it. So mathematicians have symbols. So we actually can conclude from this that the function is not even. So we can cross even off the list. Next, we need to check if it's odd. So to check if it's odd, I'm going to do negative m of x. which means it would be negative in front of the entire expression on the right of the equation, x squared plus 4. And now we need to compare these two expressions. At first glance, it might look like they are not equal, but actually they really are. So kind of as an aside over here, this is not part of the problem in any way. It's just to prove something to you. If I have something like -1/2, this is the exact same thing as -1/2, which is also the exact same thing as 1/2. If you don't believe me, you can plug all of those into the calculator and you should end up with -0.5 each time. So we're going to use the first part of this fact, and I'm going to go back to my problem now. And I'm going to move this negative sign basically up here into the numerator. The reason I'm doing that is because I notice there are negatives in the numerator. Something's not working right now. I'm trying to write with my pen and it doesn't seem to be working. Stand by. Let's see if this works now. So there's negatives up here in the numerator, and so that's why I decided to move the negative up. Distributing that -1 to each, I will end up with -x³ minus x all over x squared plus 4. At this point, if I was this imaginary student doing this problem, I would circle this one and I would circle this one, and I'd say, look, Mr. Edwards, these are the same. So therefore, m of x is odd because m of -x ended up equaling -m of x. We can circle our answer just to be a little bit more clear. And that's how you do that one. So we did in fact realize that it's odd using this process. Okay, let's do one more. Is a of t, which we'll call t squared minus t to the 5th, even, odd, or neither, neither, nor? Okay, first step every single time is replace x, well in this case it's t, with -t, replace your input with its opposite. So I get -t squared minus -t to the power of 5, which ends up being t squared minus -t to the power of 5, like that. You could prove that if you actually multiplied that out. And so then we would end up with t squared plus t to the 5th, which is not equal to the original. So therefore, this is not even. So then we would say, well, it's not even. Let's see if it's odd. You could even cross that out if you wanted. Negative in front of everything. You might hear some thunder in the background. That's pretty exciting. Okay, so after I put a negative in front of everything, I end up with this equation. And notice now that this is actually not equal to what we just got up here. These are not the same because this has a negative sign in front of the t squared. And so this means that this is not odd either. So what I would say is a of t is neither, because a of -t does not equal a of t, and a of -t does not equal a of t. And that would be the final answer. So in summary, make sure when you're doing these problems that your first step is always replace the input with the negative of the input, meaning replace x or t in the last example with negative x. And then you're going to compare with, first of all, sorry, not a, we're talking about f here, f of x. And if that doesn't work, you're comparing with negative f of x. And then if neither one of those works, then it's neither. And that concludes even and odd functions.